How do we actually go about detecting dark matter? Matter that doesn't interact with light at all. So it doesn't emit light, it doesn't reflect light, and it doesn't absorb light. Nothing. The only reason that we know dark matter is there and have so much evidence for its existence is because of our observations with telescopes, when we see its gravitational pull and effect on other objects in space. I've made a whole video on that before if you want to check it out. But if we want to physically detect some dark matter and point at something and say, this is it, this is dark matter, and if it's a particle, say, this is what its size is and this is what its mass is, how do you do that when all of our detectors detect things using light in some way? Well, we have to get a little bit clever to do this, and particle physicists have built experiments deep underground to detect, for example, the recoil energy if a dark matter particle collides and impacts with a normal matter particle. Like when the cue ball hits into a coloured ball on a pool table. Just imagine you can't see the cue ball, all you can see is the change in direction of the coloured ball. Or instead, particle physicists have also been looking out for dark matter in their particle accelerators. Again, when particles collide, but this time make a shower of other created particles, and they look to see if there's any missing energy that's unaccounted for, that all of a sudden seems to have disappeared and perhaps gone into creating a dark matter particle. But after a number of decades with no luck finding anything, all we've been able to do so far is rule out a load of possibilities for if dark matter is a particle, what size and mass it can't be, otherwise we would have found it already. That's what the coloured regions on this plot show. This is all the constraints that we have from different experiments to say it can't be this mass and it can't be this size, leaving the white regions here still unexplored. Those are the regions that are still dark matter candidates if dark matter is a particle. And in particular, these white shaded regions are the areas that we can't really detect here on Earth. If dark matter did have that specific size and mass, then actually it would have a really strong chance of interacting or colliding with a normal matter particle. And if that was the case and dark matter particles were encountering Earth, there was a very high chance that they would encounter and interact with everything and anything in the atmosphere and on the surface and in the crust of the Earth, so much so that there was no signal left by the time that you get to our big underground particle experiments that specifically try to shield from all these everyday common interactions and collisions between particles so that they can detect an incredibly rare interaction between a dark matter particle and a normal matter particle. So if instead there is a strong chance for a dark matter interaction with a normal matter particle, then you're not going to be able to detect that here on Earth because the signal will just get lost in the noise. So what about going to space instead to do this? Into the vacuum of space, far away from Earth, so you actually have a chance of isolating any signal from a dark matter particle colliding with a normal matter particle. Well, handily, we already have a detector of sorts 1.5 million kilometers away from Earth in the James Webb Space Telescope. So what if, instead of using it as a telescope, we used it as a direct detector of dark matter? That is exactly what Du and collaborators have done using JWST. Instead of using it as you normally would, as a normal telescope, letting the light that the mirror of the telescope collects focus down onto the detector, they took an image in the dark with the shutter closed or with the lens cap on, so that no light that the telescope collected actually made it to the detector. And we actually take images like this normally as we observe all the time because it's part and parcel of reducing the noise in your final science image. You read the detector when it's in the dark to get the background dark noise of the detector. The way that telescope detectors work, and any camera for that matter, is that it converts light into electric charge. A particle of light comes in, hits into the negative electrons and separates them from their neutral atoms, which produce an electric charge or electric current. The more light comes in, the more charge is generated, and that's actually what the detector records. But all detectors have like a residual background level of charge because of just heat, thermal energy, which can also separate electrons from atoms, mimicking the effect of what light does when it comes in. So before we take any images with the telescope, we record the background dark image so that we can actually measure the dark noise in the detector and remove that from our final science image. But you know what else might be able to excite electrons and separate them from atoms and produce a charge on the detector? A dark matter particle. Again, just like the two balls on a pool table analogy, if a dark matter particle came in and collided with a normal matter particle, it could transfer its energy in that collision to the electrons that it could escape and produce a charge in the detector that the detector could actually detect. Now, we as humans think we understand how electronics work pretty well, right? We've been studying it and using and improving electronic systems for just over a century now. So we have a pretty good idea, a pretty good expectation of what the background noise should be in an electronics detector from just thermal heat energy, the dark noise. And then if there's an extra signal on top of that because of dark matter, then we should be able to spot that. So just to clarify here, because I know that the terminology is confusing when I refer to like dark noise in a dark image, we're talking about the everyday definition of dark, something to do with dark matter, which in itself is a separate signal. I know it's very, very, very confusing because we're using dark in two different connotations here. But this is what Dew and collaborators have done, and here's what they found. This is the amount of charge observed by a single pixel on JWST's detector on the horizontal axis. And then the number of pixels that observe each different amount of charge is then on the vertical axis. The gray distribution is what typically people would do when they're trying to remove noise from their JWST data. But that doesn't include like cosmic rays and background space radiation that could also be hitting your detector as you're taking your dark image, your background noise image. They let people do that like separately depending on a science case. So Dew and collaborators had to account for those as well, and then we're left with the blue distribution here, which they then fit with two models. One that didn't have any dark matter interacting to produce any extra charge on the detector, which is shown by the blue curve there, and then one that did include like a possible contribution from dark matter, assuming some size and mass of a dark matter particle, and that's what the red line shows. And hopefully what you can see here is that the two are barely any different. In fact, the stats on the model fitting to the data prefer the blue line there, the model without any dark matter. So can we use JWST as a dark matter detector? Well, yes, if dark matter is a particle and it has very specific properties. Did JWST detect any dark matter though? No. But all of this work isn't in vain because it once again allows us to rule out possibilities for what dark matter could have in terms of its properties, its size and its mass. Remember this graph, right, from before, showing the possible mass and size or interaction strength of dark matter particles. All of the coloured regions were the areas ruled out by different experiments. The white areas were places that we hadn't been able to check yet. Well, Dew and collaborators have now updated a section of this plot. Thanks to their experiment with JWST, they've managed to rule out another area. That's what the blue shaded region shows here, the areas that this experiment using JWST ruled out. So what now? Well, we've got to keep thinking of different ways that we could detect dark matter, especially if it was a particle that had the mass and size in the white areas of this plot still. Now, Dew and collaborators specifically mentioned the planned Darkness mission, which aims to put a satellite into low Earth orbit, which will have a main science goal of trying to detect a possible signal from the decay of dark matter in the centre of the Milky Way. And to do that, it has a super sensitive detector that has been specifically designed to reduce that background dark noise from thermal energy in the detector. So the hope is we'll be able to do this experiment again that Dew and collaborators have done here, but with the Darkness mission once it's launched in 2026. But with greater sensitivity to be able to rule out more of these possible dark dark matter properties still in these white regions of this plot. Or maybe even, you know, a girl can dream, finally directly detect some elusive dark matter. Just a quick shout out before we get to the bloopers, because I found this research paper thanks to Astrobytes, which is a great website where astrophysics PhD students all around the world explain recently published astrophysics research papers at a level for undergraduates or keen high schoolers. It's a similar level to my videos, perhaps even a step up at times in terms of detail. So if you want something like that in your life, check it out. It's a great site, and it's how I also started in science communication as a PhD student as well. So everything I learned thanks to Astrobytes. The lens cap on. So that, okay, I think I got that fully on. Okay, I've just recorded a load of that without the microphone on. So let's go back to the beginning, shall we? To be fair, I wasn't that far through, but